allow me to reorder the teaching for chapter 7 and 8 because resistor layout is mandatory for your homework too. So I hope I would like to teach resistor first, then go back to share the experience about wireless. Actually, chapter 8 for resistor layout is also a not so big chapter. No worries. I will finish it very soon. From the very beginning, I will share the experience with you how to estimate the resistance according to the resistivity and more fundamentally sheet resistance. What's sheet resistance? Sheet instead of sheet. Okay, keep this in mind. Don't have any kind of wrong saying about this. Then I would like to tell you how to do a good enough layout for resistor. And then you need to face the variability of resistor after fabrication. Then you need to focus on the parasitics of resistor. Then we will have a comparison among all those available resistors on chip. According to resistivity, you can see the more resistivity means the more resistance for each resistor with the same size, with the same physical size. I mean the width, the length, and the thickness. Yeah. Anyway, from silver all the way, you can see the resistivity is increased. So you can see from the very beginning, humankind had aluminum for wires. The resistivity is much higher than copper. This is the reason why for the second half of point micron process, we change our mind from aluminum to copper. But why? Simply because we would like to reduce the resistance of our wires to speed up the chip operation. Then how to estimate the resistance? This is some kind of three-dimensional view of horizontal resistor. You can see we have contact to both sides, and then the main body of the resistor is here. However, I need to highlight that according to the high resistance of our resistor, the effective length is calculated from here to there. Why? Because for the other portion, it is either connected in parallel with such kind of metal contact, or for the extra tape. You can see the current won't flow in that direction. No. The current will always find the shortest cut for current conduction, right? So it means the current will definitely flow from here and all the way to the other end, then collected by the other contact. That's it. And this is the reason why we had the effective length labeled here. And it means we pay no attention to the extra overhead to the left or to the right. What is the impact for such kind of no intention? Okay. No tension means what? You don't need to have any kind of dummy layout here, over there, to prevent any kind of over action of the boundary agent. No, forget about it. Never mind, this portion is longer or shorter. It doesn't have any kind of impact on length, right? On effective length. So who cares? I don't. How about you? Neither, right? So forget about the dummy layout to the both ends. You only need to have dummy layout along this side and that side. It will be good enough to make sure that the resistor will have correct width after fabrication. Yeah, width. That's it. And how about the thickness of the resistor? Usually, the thickness or the resistivity are controlled by our manufacturer, for example, TSMC or UMC. Anyway, the detailed equation looks like this. The total resistance, the total resistance equals the resistance of two contacts, then the overall resistance of the main resistor. So it depends on not only the length, okay, it is proportional. The resistance of the main resistor is proportional to the length, but reversely proportional to the width. And then this is the so-called sheet resistance. Later I will explain. Okay? And how about the accuracy of the resistor layout? You will see, if you would like to enlarge the resistance, maybe for new engineers, they would like to apply such kind of serpentine layout for the very high resistance resistor. However, the accuracy of such kind of serpentine layout is really poor. Why? Because the variance depends on not only the variance of the length variation, width variation, right? Resistivity variation and thickness variation, all of them. You need to take care of all of them. With such kind of serpentine layout, you will get a lot of variation according to the length and the width. It doesn't make any sense. So for accurate resistor, don't have such kind of serpentine layout. All right. If you really need a high resistance for your resistor, then please, you can connect a lot of unit resistor in series. That's it. That is the only one way to create such kind of high resistance for the resistor. And how about the connections? I'm talking about the contacts and vias. Actually, they also provide quite high resistance. You need to take all of them into consideration. Why? Because the size of the via of contact actually is quite small. Then according to the resistor, you will know it equals the resistance by length and divided by area. Okay, you can see the current will flow in this direction or that direction. So the area of such kind of via or contact actually is quite small. For small area, it means large resistance, right? That's it. Allow me to show some of the real values for contact resistance from 1 micron to 0.35 micron. You can see how many generations from 1 micron to 0.5, okay, and then 0.35. Wow, there are already 2 generations in difference. But how much difference in resistance? Almost none. You can see for the via between metal 1 and metal 2, it is 5 in 1 micron process. It becomes 6 is 0.35 micron. Why? According to scaling down, the size, the area becomes smaller than before, even though the material is changed, is enhanced in resistivity. However, the size of the contact of vias becomes much smaller than before. So you can see almost no change in the contact of via resistance. I think the tendency, the trend is some kind of warning for you guys. Never mind what kind of process you will use. The resistance for each contact or via will be about the same as the previous generations. You can take 1 micron or 0.35 micron for a very good example. No change, no much in change. Okay. Then, how many kinds of resistor on chip you can have? Usually, we have poly resistor, just like this. We use polysilicon to be the main body of our resistor. And as I mentioned moments ago, you need to do dummy layout along the length of the resistor. But you don't need to do any kind of dummy layout here or there, because I told you already, the extra portion here, the extra portion here and there actually has almost no impact on the real resistance, right? Because they don't have they almost don't have any kind of impact on the effective length from here to there. Okay, that's it, no more. And this is the reason why only dummy laid out both sides, but not at both ends. Okay, this is one of the very good example for resistor type on chip. Then, if you would like to get the highest resistance for the resistor, usually you can use well resistor. Why? Because well is doped very, very lightly. Lightly doping always means very high resistivity, right? So that's it. However, nothing is free. You need to pay for it. Pay what? For such kind of high resistance oil resistor, you need to sacrifice the performance. I'm talking about the variation and the quality of the resistor. For well resistor, you need to face a lot of temperature effect. And after fabrication, to my memory, its variation is the biggest among all those on-chip resistors. So it's up to you. You can use such kind of well resistor with very high resistivity, but you need to sacrifice the performance. Okay? And then we can use the other one called diffusion resistor. Diffusion means what? What kind of area will be diffused? Usually source or drain, right? It means they will be doped or imprinted to be N plus or P plus. So the conductivity for such kind of diffusion resistor is much higher than well. It means the resistance will be reduced very much from well resistor. However, the performance of such kind of diffusion resistor will be much better than well resistor. Again, it's up to you. Anyway, if you would like to get the best performance for your resistor, usually we focus on this. Poly resistor usually is the best for the performance, but according to the resistance, it is usually much lower than well resistor. So you need to pay the price. What kind of price? Larger layout area for poly resistor. That's it. Let's go further. Sorry, I skipped chapter 7 for wiring, right? For humankind, we would like to speed up the operation of your chip, and it means that we need to reduce the parasites for not only your main devices, but also the wires to connect all of them, right? How to speed up the device? We have two kinds of technology. It is called silicization and silicization. For silicization, it means we would like to reduce the polygate resistance. But how? Just above the surface of the polygate, we would like to have some kind of metallic compound of silicon, just like tantalum silicide, tungsten or titanium silicide. 氮啦、钨啦、钛啦，我们可以用各式各样的那个金属化合物，把它们长在 gate 的正上方，因为它们是并联嘛，所以它们的有效阻抗 gate 本身的有效阻抗就可以被大幅降低。Because all those silicization is fabricated above the surface at the top of the gate. So they are connected in parallel. I mean, the main body of the gate and such kind of silicization, they are fabricated in parallel. So it means the overall resistance will be substantially reduced with such kind of silicization. Anyway, if you only speed up the operation of gate, it is not sufficient. We can also speed up the operation of your source and drain. But how? You need to do the same thing, right? You need to have such kind of metallic compound of silicon over the surface of your source and drain. So if you do all of them, I mean have such kind of metallic compound over the surface, above the surface of gate, source, and drain, we call it silicization. It means self-anide silicization. That's it. That's what TSMC or UMC can help to reduce the parasitic resistance to speed up the device. I mean the most important device, MOSFET. However, if you would like to apply them for resistor, then you need to face a big problem because according to silicization or silicization, the resistivity for your gate is what? Polysilicon. Or your diffusion, the source and drain, will be substantially reduced. It means again, the resistance is reduced, right? It means you need to sacrifice a lot of chip area for layout to achieve the same amount of resistance for your resistor. Wow, that is a big problem, right? How to solve it? Later, I will tell you all the secrets. Here is what I mentioned for silicide polyresistor. You can see above the poly surface, never mind that is N plus or P plus, we have another layer that is some kind of metallic compound, right? To reduce the overall resistance. Because this layer and polygate, they are connected in parallel, right? Maybe you will be so curious why we have such kind of N plus poly or P plus poly. Very simple. In NMOS region, I told you from the very beginning, in chapter 2, right? I told you we need to fabricate polygate first because it needs to protect the underneath channel, right? So after you fabricate polygate, then you can diffuse or implant your source and drain, right? So for PMOS, during such kind of implantation or diffusion, source and drain will become P+. However, poly is above channel. Poly is used to protect the channel. And it means all the diffusion or implantation will happen at poly. So poly will become P+. Oh, sorry. Poly will become P+ here for PMOS area. And similarly, it will become M+ after N-type doping or implantation in NMOS area. This is the reason why we have such kind of M+ poly and P+ poly. For such kind of M+ or P+ poly, the sheet resistance. Oh, sheet means what? A square. Okay, a square layout for any kind of resistor. We call it. The resistance is called sheet resistance. So for such kind of M+ or P+ poly, the sheet resistance is 3 to 5 ohms. The process dependence is about 60 to 70% in variation. I have no idea whether or not this figure is correct, but to my memory, at least around 30 or 40% in variation. All right, maybe not so large, but at least tens of percent for variation. It's quite huge. Then according to the temperature coefficient, you have the TC. The temperature coefficient is about positive 0.2 to 0.4% per degree for every in variation. That's it. For such kind of poly resistor, why I told you the performance is the best because it gets the smallest parasitic capacitance, simply because it is far away from such kind of P substrate. Substrate is quite noisy, right? So as far away as possible. Similar condition happens for diffusion resistor. You can see again, according to sedimentation, we have such kind of metallic compound above the surface of your M+ resistor or P+ resistor. In this way, the sheet resistance is also reduced very, very much from the original one. Which is the original one? I mean, without sedimentation or sedimentation. The resistance is supposed to be much higher than this. So you cannot please everybody, right? TSMC or UMC would like to speed up the operation of our main device, I mean MOSFET. They help us to have such kind of metallic compound over the surface of our source, drain, and gate. However, if you would like to use such kind of area for resistor, you will complain, hey guys, don't help me have such kind of sedimentation or sedimentation. What you can do? Stop them. But how to stop them? You need something called black mask. All right? Such kind of mask can be used to stop sedimentation or sedimentation to get much higher resistance. But again, nothing is free. You need to pay for it. For mask, it is really, really expensive for advanced processes. It's up to you to use it or not, to be or not to be, to see or not to see. That's your own problem, not mine. Okay, let's go further. If you would like to get high enough resistance, but you wouldn't like to pay such kind of price, I mean for extra black mask, then you can apply such kind of annual resistor. Yeah, for each square, it can help you to generate 1K ohms. It's really high. However, the performance is not good. According to temperature coefficient, it gets the biggest variation. I mean, among all those resistors you can use on chip. Not only that, but also the resistance of N-well depends on voltage very much. It means what? If you change the terminal voltage, then you will also change the effective resistance of such kind of N-well. Wow, it's really troublesome. So that is the biggest, that is the highest resistor. But you need to use it with much attention. Okay? For N-well resistor, we have quite much p-n junction. That is some kind of cross-sectional view here. All right. So you have p substrate and a lot N-well. According to such kind of p-n junction, you will have the so-called leakage, junction leakage. How to stop it? You can apply P plus diffusion all around the region. Okay, again, cross-sectional view for you. With the help of P plus, it can help us to push away such kind of p-n leakage, because P plus is with much higher doping than P minus substrate. All right. It can reduce the impact of such kind of p-n junction very much to reduce the leakage. Then, as I mentioned, if you hate such kind of citation or citation to reduce your resistance, then you can stop it. You can prevent it by using the so-called black mask. For example, above the surface of your polygate, you can have such kind of citation black mask. And after fabrication, you can see, wow, see here for polygate, no metallic compound here, right? So it really means the overall resistance in this area will be much higher than the other area. In this way, we can enlarge the resistance very, very much. Here, allow me to show you. With such kind of citation black mask, the resistance can be increased from only a few ohms. Let me go back. See? Wow. It is increased from 1 digit to 2 or 3 digits, right? To 50 over to several hundred ohms. It means the resistance is enlarged by 2 orders, simply with citation black mask. And look, it looks quite easy, right? But it is really expensive, because I told you, you need one extra mask called citation black. That's it. If you like it, pay for it. It's your own business. Instead of mine, it's up to you. Anyway, I would like to highlight it again. To enlarge the resistance for polyresistor, you need extra citation black mask. Extra means what? Extra money. Okay? Extra price. So M plus or P plus poly without saturation or saturation, you can see for P plus, it is around 2 to 400 mole per square, and for N plus, according to its higher diffusivity, to memory mobility. Sorry. For N type, the mobility is 2.5 to 3 times higher than P type, so the resistance is reduced by the same amount. That's it. Okay, for your reference. If you would like to enlarge the resistance to make it even higher, then what you can do? Please have a look such kind of detail. We still have N plus or P plus doping. N plus or P plus doping is good for conductivity. However, on the contrary, it's really bad for resistivity. So, if you would like to enhance the resistivity further, in addition to silication block mask, you also need to block such kind of N plus or P plus doping. It means you need extra and other extra block mask to stop diffusion or implantation. See, that is what I mentioned moments ago. You need two extra masks, one to block silication, one to stop P plus or N plus doping. Then you will get such kind of very high resistance for your poly-A, for your polysilicon. Without silication, without implantation or diffusion, bingo, you can achieve very high, almost the highest resistance among all those on-chip resistors. So we call it high resistance resistor or high HR polyresistor. Okay, HR means high resistance. For each square, it can help you to generate more than 1K ohms, as high as NOL resistor, but the performance is much better than NOL. However, you need to pay for it. The price is sky high because it needs two extra masks. It means you need two extra costs to have such kind of HR polyresistor. Again, it's up to you. I cannot help you to make the final decision whether or not to apply such kind of HR polyresistor. It's really expensive, to be honest. Then you need to focus on such kind of parasitics. Especially if it is close to substrate. You need to be very careful. It always induces quite large parasitic capacitance. Okay? Then allow me to show you the resistor model. Where is a resistor itself? Here. This is what you want. This is what you need. In addition to what you want, you will face a lot of parasitics. Wow, it's very complicated. To be honest, you don't need to memorize all those parasitics. That is not what I require you, what I recommend you to do. No, I would only like you to pay attention to so many parasitics. Pay attention to so many. It means what? If you have wrong or bad layout pattern, you will induce a lot of parasitics for your resistor. It doesn't make any sense. The overall performance will be substantially reduced. So please have very good, very neat layout to reduce the parasitics. 我其實冇要叫恁大家甲背起來這個 model 實在是太複雜了啦。我是要甲恁建構，就是講 你若是做中摆的布局的话，你可能会得到一拖拉库的杂散成分，毋是干那杂散电阻尔吼，你会看到一大堆的迄个杂散电容甚至你会看到即个杂散电感足恐怖呢，非常的恐怖，恐怖真恐怖奇怪，伫什么状况之下，你会看到即种神奇、非常神奇的杂散电感就是我头早甲恁讲的啦，大蛇状的布局这实在是有够惨的、够弱，你千万毋通去做迄种我这歪歌必白的布局方式啦越简洁越简单，杂散成分会越少。OK，Anyway， this is what you need, and for all the others you hate, right? The neater, the simpler your layout is, the less parasitics you need to face. That's what I can recommend you. Maybe you will be curious why I have such kind of parasitic inductance. Very simple. Moments ago, I showed you such kind of serpentine layout, 大蛇状的布局，with such kind of very weird layout. You need to face quite much, I can say at least a few parasitic inductance. It is really harmful for your resistor, right? So please, to make your layout as simple as possible, as neat as possible. 让你的布局越简单、越精简越好了。Okay, even for the main resistor you need, there are still quite many, how can I say parasitics? Quite many parameters which will scale you. 你会驚到Why? Because for new engineers, they always think, what is the main resistor? Actually, it is the schist resistance by the length and over the width. But according to side etching, right? The effective width actually is what you draw, the width you draw minus side etching 因为有那个测试的缘故所以你画的宽度实际上会小一点delta W 就是因为测试效应所造成的。Anyway, W is the width you draw, but according to a side diffusion, you will get such kind of delta W. You need to subtract it to get the final effective width. How about the length? Maybe you will be curious, why not? There is some kind of minus delta L. I told you already, because the length is calculated from the contact to the other contact. So we pay no attention to the delta L. Here, over there, we simply don't care. Okay? That's it. Anyhow, this is what you can imagine from the very beginning. But you still need to face the other two effects. The first effect, we call it thermal effect. You need to face temperature coefficient 1, means the first order temperature coefficient, and the second order thermal coefficient or temperature coefficient, as you like. Alright, so means what? Usually, for all those resistors, they have such kind of TC1. Maybe they don't have TC2. It means we don't have such kind of curvature according to the temperature effect. But all of them, I guess, have TC1. So it means what? According to the temperature, if the temperature is changed, so does your resistance. Wow, it's really bad, right? Only if the temperature is changed, your resistance will also be changed. It really means that the absolute value of your resistor is not important. If your circuit depends on the absolute value of the resistor, then you need to face the consequence. You need to think again. Think more. According to temperature, is it possible for you to stabilize the temperature for your device? Usually, it is not the case. You have no way to stabilize the temperature during operation. For voltage, yes, we have regulator to help you stabilize the supply voltage, but we don't have any kind of temperature regulation to stabilize the temperature for you. So it means after power on, the operation temperature for your chip will be increased by default. And after such kind of temperature increase, you need to face some kind of variation for your resistance. It means it is really hard for you to stabilize, to keep your resistor, your resistance constant. No way, no way. What you can do to make your circuit depends on relative resistor, relative resistance instead of absolute resistance. For example, if the gain look like this, then you don't need to worry. Only if you match the layout for both R1 and R2. Then according to temperature variation, yeah, the resistance for R1 is changed. So does R2. And according to such kind of relative dependence, don't worry, the final result will be exactly the same. Okay? That is the secret. That is the power for relative resistance. But don't touch absolute. Absolute resistance is no good for your own design. Okay? The other bad impact is here. The resistor actually has not only temperature dependence, but also voltage dependence. It means that the terminal voltage, if the terminal voltage is changed, your resistance is also changed. Wow, that is really, really bad. Okay, again, to my memory, some of the resistor has VC1. Most of them don't have VC2. Okay, anyway, anyhow, for the first order temperature dependence or first order voltage dependence, they are troublesome enough for your own design. Never mention about the second order temperature coefficient or second order voltage coefficient. They are even harder to deal with. All right. So please choose the resistor with the least temperature coefficient. And hopefully such kind of resistor doesn't have any kind of voltage dependence. Otherwise, you need to think again how to deal with such kind of voltage dependence. Anyway, as a good teacher, I can tell you one way. Okay? How to deal with such kind of VC1 or VC2? This is some of the secret. For example, for a long resistor, you can divide it into 10 small ones, right? But connect them in series. So you have R here, you have 10 R there, but 10 of them in series. You still get the same R. However, with such kind of serial connection, congratulations, the voltage for each resistor is reduced by 10, right? Here you have V, there you have V over 10. And you can see the impact of VC1 is reduced by 10. And how about VC2? Oh, it is reduced by 100. Congratulations. Even though your resistor has VC2, with such kind of serial connection, I promise you, you can totally neglect VC2. Okay? That is the power of sub-devices. If you divide such kind of main device into many sub-devices, then connect them in series or in parallel. For capacitor, you need to connect them in parallel. But for resistor, usually you connect all those sub-resistor in series. In this way, you can reduce the impact for VC1. Even more reduction for VC2. Bingo! That's it. Maybe you will be curious how much all those temperature coefficient or voltage coefficient will be. Allow me to show you some figures from TSMC 0.35 micron process. I got help from my student maybe more than 10 or 20 years ago. You're seniors. 我请你们学长帮忙一下哈，把台积电点35的那个制程资料抓出来。Okay, let's have a look at for such kind of very old, very mature process from TSMC, how much resistance per square you can have from P plus, N plus, 80, 150, and we're all around 1 kilo, right? Poly 1 only 8 because it gets some kind of sedimentation. How about Poly 2? No, because only Poly 1 in 0.35 micron is used as gate. How about Poly 2? It is not for gate. Alright? So, not so important as Poly 1. It means TSMC or UMC would like to save your money. Even silicidation or sedimentation. You need to pay for it. Right? So, for Poly 2, since you cannot use Poly 2 to be the gate, who cares? I don't. Right? Anyway, anyhow. How to reduce, so it means the resistance for Poly 2 is much higher than Poly 1 without silicidation or sedimentation. But how can you reduce the resistance of Poly 2? Very simple. You can have as many contacts as possible to connect your Poly 2. That's it. All those contacts will be effectively connected in parallel with Poly 2 to reduce the overall resistance. That's it. Okay, in brief, who gets the best performance? No worries, Poly resistor. For example, Poly 1 gets the smallest temperature coefficient. And how about VC1 and VC2? Almost zero, right? Minus first order, minus fifth order, forget about it. Almost zero, just forget about it. On the contrary, who gets the worst performance? Yeah, no doubt. And well, even though it gets the highest resistance, but according to TC1, it is the highest, right? Even worse, it gets TC2. For all the others, they don't. So it means what? For temperature variation, and well, we'll get not only linear change for the resistance, but it gets some kind of second order change. Wow, that is really bad for your own design. Again, don't touch. It means unless you have no other better choice, otherwise don't touch MWell because the performance is really bad. Only if, okay, for some case, you only need Large enough resistor, you don't need to pay attention to the property, to the characteristic of the resistor. Then you can apply NWell. Okay, only if the resistance is large. That's it. You can use NWell. For many of the other applications, I told you already, don't touch. About the accuracy, for your reference, I have no idea whether or not the accuracy is correct or not. If you are curious like me, please go back to read the technology files by yourself. And allow me to warn you again, this is only for 0.35 micron. Okay? This is not for any the other process like 0.18 micron or 90 nanometers, blah, blah, blah. Sorry. They have their own resistance, their own temperature coefficients and voltage coefficients. Here's some kind of simple guidelines for resistor. If you would like to match more than one resistor, then you need to use E-cross structure. That is what I told you, unit device. You need to use unit resistor or sub-resistor connected in parallel or in series. Yeah, to match more than one resistor. And the resistor cannot be too narrow or too short. You are better to have some kind of interdigitization. For example, you have R1 and R2, right? So you have 1, 2, 2, 1, 2, 1, 1, 2, blah, blah, blah. Yeah, and also you need to pay attention to thermal effect compensation. For later slides, I will tell you how to do such kind of temperature compensation. For good temperature coefficient, please choose a poly or N plus P plus. For absolute value, nothing is good for such kind of absolute resistance unless you have the so-called calibration or trimming. Otherwise, again, don't touch. Okay, you need to make your circuit depends on the relative value instead of the absolute value. Absolute value means absolutely inaccurate. 绝对值意思是什么？绝对会错误就对了啦。最好给我不要碰哈。Alright, as I mentioned, to highlight the accuracy, yeah, you need to have such kind of unit resistor and then connect them in series or in parallel, as you like. For absolute accuracy, I mentioned already, more than tens of percent in variation. It is no good for your circuit design. However, for relative accuracy, if you do very good layout pattern, 1, 2, 2, 1, 2, 1, 2, blah, 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 for such kind of machine layout, it is totally possible to reduce the variation from absolute tens of percent all the way to relative less than 1%. It is totally possible. But again, you need to use unit resistors, connect them in parallel or in series, and also have very good interdigitization layout, common-centric layout, blah, blah, blah. And how about the resistance of your wire? Again, you can estimate it. Yeah, just like this is 1,9, right? So again, for the resistance, it looks like this. Sorry. Right? This is the length. And how about the area? Area means the cross-sectional area. 截面积. And what is that? The width by thickness. Okay? So you will have this W and T thickness. That's it. All right? What you can control? Actually, you can only control W and L, right? And what you cannot control is resistivity, and thickness. So allow me to rewrite it. You will have those terms you cannot control, and this term you can control. If you make your length and width the same, it means you have a square layout just like this, right? Then W over L will become 1. They cancel each other. So finally, you have sigma over T. That is the so-called sheet resistance. And I also have such kind of R square, easier for you, right? For you to memorize it much easier than before. I call it R square. Actually, it is the so-called sheet resistance instead of sheet resistance. No. It is sheet instead of sheet. Okay. Then, if you connect the square 2 by 2, yeah, you will see R square, right? And for all those 4, how much you can achieve the same R square? Yeah, because you have 2 R square here, 2 R square there. Connect them in parallel, you get R square. Yeah, see? You have 2 R square in parallel with the other 2 R square, and finally, you still get R square. It means what? In theory, never mind how large the layout is, just like 2 by 2, right? You have 4 times larger in layout area, but the ideal resistance is still the same. Okay? I mean, for the 4 times larger one, you still have the same R square. So, do you need to spend a lot of area for such kind of R square layout? It's up to you, according to power consumption. All right? 2 major constraints. You see, for this resistor and 4 times larger resistor, they have the same resistance, R squared. You may think, oh, it means I can reduce the layout area but still keep the same resistance. Is it correct? Yes. Then you can do it again and again, right? To become so small, to become even smaller. Does it make any sense? No. There are 2 major concerns you need to consider again and again for very small area during layout. First of all, according to random mismatch, as I mentioned again and again, the smaller area means what? The larger random mismatch. So it means the accuracy for your resistance will become much poorer if you reduce the layout area too much. That's your first issue. And how about the second issue? The second issue related to power consumption. The smaller area means the less power consumption capability, right? If you need to consume a lot of power or to conduct a lot of current, please use large area for your receiver layout instead of the small ones. Otherwise, they may be burned out during operation, during high power operation. Got it? So again, before layout, you need to think twice. How much area you would like to sacrifice for your layout? it depends on how much random mismatch and how much power consumption the resistor needs to carry. Okay? Then you can make the final decision. Bingo. For some wire pattern like this, from here to there, I have some kind of estimation. You can see, yeah, 2, 1, and 2. What is 3.5? 1, 2, 3, and 0.5. So it means, how about the corner? 0.5, only for approximation. Okay. My recommendation is, if you would like to do real layout for your resistor, please don't have such kind of U-turn. It is no good. All right, because don't tell me the real resistance is 0.5 R-square. I don't buy it. It is not the case. Okay, that is only something we call approximation or estimation. This is not any kind of real value. So it means what? You won't have accurate enough resistance for such kind of L-shaped resistor. Don't do it. And how about the other ones? Forget about it. Okay, even though we have some kind of estimation, approximation for you, but I still recommend you not to do such kind of CV layout. The only layout pattern making sense is something like this. Rectangular is always the best. That's it. If you consider the accuracy very much, please only focus on this. Don't touch all the others. Never mention about some kind of U shape or V shape. Forget about it. However, for some special cases, if you really need such kind of layout, then the U shape is much better than this, because you have very sharp turns. 有非常尖锐的转弯哈，这个是不好的。That is no good, especially for high frequency operation. Such kind of sharp turns will hurt your high frequency operation. Okay, because the current is very hard to turn around here or to turn around there. To make the U-turn smoother, okay, to make it as smooth as possible, you need to have such kind of curved layout. But it's troublesome, right? So forget about it. Forget about it. If possible, don't use this or that, because it's troublesome to make it. If you really want it, you may have such kind of 45 corners or rounded. All right, rounded is the best for such kind of U-turn, but sometimes it is not allowed by your EDA. Then instead, you can have such kind of 45-degree corners. This is 90 degrees, too sharp. So what is 45? Okay, something like look like this. Okay. Do it by yourself. Don't bother me. Then how to compensate such kind of temperature effect? Okay. For example, you have R1 and R2 to be matched, but you have some kind of power device, power source. The temperature gradient in theory look like this. You can see R2 needs to face higher temperature than R1. According to temperature coefficient, the resistance of R2 will be higher than R1. It doesn't make any sense. How to compensate for such kind of temperature effect? To make the layout for both according to isotherm. Okay? According to isotherm, R1 and R2 will face the same temperature effect. So it means never mind how much TC1 or TC2 they have, according to the same temperature impact, they will have the same relative accuracy. No worries. Okay? That is what I can help for temperature compensation. We need not only to face temperature variation, voltage variation, but also stress variation. I mentioned already. Because the silicon lattice is anisotropic, 非等向性的, and means not. It is not isotropic. So it means along different angles, along different direction, the resistance will be also different. According to stress, in which direction you can reduce, you can get the minimum impact from such kind of stress. Yeah, along 45 degrees. But again, it is troublesome for your layout because usually this area and that area will be wasted. I don't think you will have the other device layout here or there. So those two areas will be simply wasted. So that's it. According to stress, my only recommendation is, for example, R1 and R2, they all laid out in the same direction. For this or for that, then they will get the same impact from stress, good enough for relative accuracy.